All right, I'm in Roblox now. So I am going to be putting the informal into the phrase informal event for today. Um, I'd love to get lots of chat, lots of people talking, um, making comments on what I've said. So please feel free to jump in, say, Will, that makes no sense. Will, that's vague. Will, have you considered this, etc. And that'll be really good for me, and I'm sure for everyone as well. Okay, so the general topic is going to be quantum computation, but I want to say first and foremost that I know absolutely no physics whatsoever. Kinetic energy? Nah, never heard of it. I don't know what you're talking about. Um, so I'm coming from a very mathematical perspective on this, right? And in fact, I think that's probably like one of the benefits that I have to offer on this talk. So there's a few resources out there that kind of do this. Um, but it's helpful having someone that you can speak to about it, where I'm hoping to kind of do this like a mathematics lecture, right? I'm going to be like, oh, here's a definition, and it's going to have like a very suggestive phrase, right? But then the mathematical object that I'm going to associate to that definition kind of begs a question, kind of begs like, okay, so why is that that? So, for example, my first definition, so a state space is a Hilbert space, right? So this is kind of what I mean. Like, well, but Will, we already have a definition for Hilbert spaces. Like, what is the point of a definition? A state space is a Hilbert space, right? And then even if you accepted that, you would be like, oh, okay, cool. Well, clearly state space. That's obviously talking about some kind of circumstance that you're under, right? And your imagination kind of goes wild. You're like, oh, well, surely this is some kind of physical apparatus. Like I've got some set up here and it's a dynamic system and things are interacting with things, and at any like discrete time step it's in some kind of state, and then all of those different states are described by the state space. Oh wow, and Will's telling me that that's a Hilbert space. How mathematically and physically fascinating. Why is it that this physical concept is just nailed perfectly by the concept of a Hilbert space? Yeah, like they're all the exciting questions of the interplay between physics and mathematics, right? And for sure, you can go and ask those questions, and there's deep, complicated answers to it, and very large textbooks dedicated to that pursuit. Um, but the point is, we're actually not going to be doing that. Like, I want to be getting to the point where we understand these kind of as mathematical definitions, and then by the end of this, you can like use the terminology of the physicists, and you can solve some problems, and you can understand some examples and things like that, but you don't actually understand the full history of why a like few decades worth of thought experiments led to these mathematical definitions, right? Um, and we will be well, like, actually, one thing I'd really like to kind of pose to the audience or anyone that has an opinion on this or anyone that feels like they can comment. Um, from my reading at this point in time, it seems a little bit like even the physicists are a little stuck on this, right? Because the intuition that you have towards quantum mechanics is kind of not even there, right? So when you're trying to do quantum computing, you're kind of using these mathematical objects and they describe some kind of physical phenomena in some way, somehow, right? But even if you understand the physics, it's still like a real challenge to get your head around to the point where you see why this mathematical concept is the rigorous formalization of that physical property. So I do wonder actually just how much the physics actually helps you. I wonder if you get to a point where you're like, oh, well, of course a state space is a Hilbert space. What else could it be, right? So, but at the end of the day, we're all kind of like talking with these like kind of definitions, and we've accepted that these are the mathematical constructs that correspond to them. So I'm just going to be going ahead and giving you those. Uh, quantum computation is not my main research area either. It's something that's just come up in my research, and I'll probably talk about that a bit at the end if I have time. Okay, cool. So that's what a state space is. What's a measurement? So a measurement is actually going to be a family of linear operators. So bounded linear operators if the Hilbert space is infinite dimensional. So a measurement upon a state space. And they need to satisfy a few things. So the first thing is the so-called completeness equation. So this then, oh, psychedelic. Okay, how do I get rid of that?
Just hit undo. It should have hopefully get rid of it.
I think it might exist in the outside world, but we'll see.
There's a bit of a bug there apparently.
That's all right. Okay, cool. So, well, actually, this is the only condition, but then there's going to be a few other quantities that come out of this definition, which are going to be as well. So let me just explain this equation. I need lowercase m's here, right? So we've just got this family of linear operators. I can go ahead and take the duals of those operators, right? And that's what m dagger is. And then I can multiply that by m itself. And I just want the sum of all of these to be the identity matrix, right? So I'm about to associate another number to a measurement, and that number is going to be thought of as a probability. And this is the thing that guarantees that the probabilities sum up to 1.
You mean adjoint,
so
not dual?
Oh, yeah, sure. Adjoint operator, dual space. I need to make an eraser. Okay, moving to another whiteboard. Okay, so associated to a measurement.
You went the reverse way to the way Ben was going, but that's all right.
Well,
you're a left-handed person, are you?
No, it's memory cues, right? Like clockwise is going to mean one of our talks, anticlockwise will be associated with the other. It doesn't matter in any way, does it?
It matters. No, it's okay.
Oh, what's okay? Do you want me to move over to the other one?
I'll deal with it. It's all right.
All right. Yeah, so associated to every measurement and element of your Hilbert space. Oh, let me just say this. Is a quantity, suggestively denoted by P. So P of M is to be thought of as like the probability of outcome M occurring inside your measurement, right? And it's the inner product. Cool. And then the last thing that you want to keep in mind is there's also kind of the result of this measurement, right? And again, I'm kind of leaning into the same thing that I said at the start of the talk, where this is in some way the result of the measurement. I have absolutely no idea how it is that. But here we're just going to be thinking about this as a mathematical definition. So I'll say also there is the resultant state, which is this, right? And so this is the whole like game. It's like when you do the measurements, you might change the thing that you're taking the measurement of, right? And this is what it becomes. And there might be certain types of measurements that you can perform where that thing actually doesn't end up changing the element. I guess I'm going to be calling them qubits. So these things later, I wanted that to be green. So elements of the Hilbert space C2, you want to, there are particular measurements so they're not going to end in like a result that changes your qubit. And they're the ones that you want, right? Because it's like you perform some measurement, but it doesn't actually alter the outcome. Or it might like jump it around a little bit, but it ends up back where it started off. And they're the kind of measurements that you want to be doing when you're looking at like quantum error correction, for example, right? Because in quantum error correction, it's like you receive your code and you want to check whether there's errors for this code, but you don't want that check for errors to like destroy the code even further. You know what I mean? So what you want to do is you want to come up with these measurements so that at the end of the day, I've extracted information about whether an error occurred or not, but I want to do so in such a way where I don't actually alter the message that I received. And so that's what the game is. And this is why this is a mathematical game, right? This is why you're able to get into this without knowing any of the physics. You can just accept this and you can say, oh, okay, so this is how I encode stuff. This is how I measure it. This is the impact of that measurement. So what can I do and what can't I do? And how can I do clever things involving error correction, etc. And that's kind of the whole point. Okay, so moving to the second board. What I have been told is the second board.
Yeah, you just admitted you were doing it wrong, right?
Yeah, that's that's the fear of public speaking, isn't it? All right, so there's a special type of measurement, which are the so-called projective measurements, and these things are kind of simpler. They're the ones that come up most in error correction. So I'm going to be talking about these. These are a little bit harder to swallow, I think, because it makes you say, okay, why is this what the previous one is? And there is a theorem there, but I don't know. If I was honest, I find that theorem kind of unsatisfying. I'll talk about that though. So let's get into this definition. So is that heavy breathing indicative of upsetment at a statement I've made?
No.
It's still stuck on the fact that I used board 2/3. All right. A projective measurement. This is not like adjective noun, okay? This is one noun. So a projective measurement is not a particular type of measurement. It's a new thing. On some state space. This one is a Hermitian operator. A Hermitian operator is an operator which is self-dual. Sorry, I keep using dual. Self-adjoint, right? So it's just take the adjoint of its corresponding matrix and you get the exact same thing. In the special case of a finite dimensional Hilbert space, the adjoint of an operator exists in an arbitrary Hilbert space. You just ask, is that operator the same as original one? If so, we have a Hermitian operator. So this is M. Okay, so it's a theorem from linear algebra that if your operator is such that M adjoint, so the composition of those two things is equal to M adjoint M, then that thing admits a so-called spectral decomposition, which is simply a diagonalization, right? Are such things. And so we have that M is diagonalizable. We can write that, so we can say that this is the sum over some collection. The collection is the eigenvalues, right? And then Pm is the projection onto the mth eigenspace, right? So I can write that. go away.
Yeah, it seems like the palm rejection's a bit of a problem, so you sort of need to.
Yeah. And
Eraser to the rescue.
Yeah, that's right.
yeah, I was about to say the ironic thing is the more you do it, the more stressed you get, the more your palms sweat, the more it does it. So it's a bit of a self-fulfilling prophecy. Well, recommended that you have a towel with you. Maybe I should wear my gloves. Okay, I'll put my glove on and see if that helps. Okay, so we just projected onto the nth eigenspace there. And then here, again, we have these associated quote-unquote probabilities, but I am, like, not convinced that this thing is non-negative. And that's a question that I currently have about this work. But this is similar to the measurement case, but we don't take the adjoint. It's just PM. And then the resultant states. Again, this is similar. Cool. Okay. So, yeah, these are the measurements that I'm going to be using in the example that I'll give when we're actually looking at quantum error correction. So, the theorem essentially is that projective measurements and measurements are equivalent, but the problem is that's really being generous with the word equivalent. So, if you allow yourself, what do they call it? Ancilla, I don't know how to pronounce it. An ancilla space. Ancilla. Okay, thank you. So if I take a projective measurement, that's upon some state space, H, right? Now, ancilla, that's not a name, that's an English word, and it means like in the aid of, right? So it's kind of like I can introduce this extra thing, and then extra thing is a Hilbert space, so call that Q, and I can consider Q tensor H, and then I can essentially simulate a measurement with a measurement on H by a projective measurement on Q tensor H. But you also need to be able to multiply by unitary matrices. And in the world of quantum computing, unitary matrices are kind of allowed because they're the analog of logic gates inside the classical world. So you all know the story with like a classical computer, right? You've got these AND gates, you've got these OR gates, you've got these NOT gates, and then you can string them together in these like the Boolean algebra diagram things. You've got all of your inputs on the left, and then these go through gates. And you end up with an output over here. So in quantum computing, you do the exact same thing, but these gates are described in some way by unitary matrices, right? And then again, there's another statement which I yet to understand, which is that all unitary matrices, 2x2 complex unitary matrices, describe a valid quantum gate on a qubit, right? And so that's literally the game when they say quantum computing. So like, what can you compute with a quantum computer? Well, it's, what can I compute using these quantum gates, right? So it's exactly analogous. But anyway, the point is you need to accept that in order to understand the simulation. And even once you accept that simulation, you also need to project back onto H if you're truly on H. And I'm not completely convinced that that's actually that easy. Like, I'm not convinced that really truly comes for free. But anyway, that's the sketch of the proof of my misunderstanding. Hopefully that's helpful.
Okay,
maybe. Yes? Okay, coming to my first board again. No matter what opinion you have on the orientation, we're in the first board. I'm actually just going to jump ahead to the example that I had because I think I'm a bit short for time, and this is kind of the meat of it anyway. Okay, so what do I actually need? So there are these there are these particular gates which are the Pauli matrices, but you know what? I don't even need all of them. So I'm going to be like unbelievably low to the ground here. Okay, so even if nothing made sense so far in the talk, just like riff with me here. Like let's just draw some stuff on the board and see if we have an aha moment. Okay, so I'm going to consider a Hilbert space, and the Hilbert space is going to be the complex number squared, right? C2. Okay, I'm going to let Z be the following complex matrix. 1, 0, 0, -1. Okay, and then I'm going to consider a 3-qubit system, which simply consists of H tensored by itself 3 times, right? So I'm going to be looking at, I'm also going to be calling elements of this space qubits. So I'm going to be looking at qubits inside this state space. I'm going to say, has there been a bit flip error? Has a 1 turned to a 0? Has a 0 turned to a 1? And I'm going to see if we can work that out only using projective measurements. And and in fact, I'm only going to use this Hermitian matrix Z here. Okay. But I'll tensor it by itself a few times. So I need this convention where it's like I'm gonna be using these operators Z1, Z2, and I'm gonna be using Z2, Z3, and Z1, Z3, but they all fall in the same pattern. This just is shorthand for tensor Z, tensor the identity matrix, right? So I just perform Z on the first 2 copies of H, and I don't do it. And then similar for Z1, Z3, and Z2, Z3, right? Okay, cool. And what I'm going to do is I'm going to say, consider a qubit psi that has had a bit flip error occur to it. So what that might look like is say the second bit has been flipped, right? So in some way, somehow, this used to be A 0, 0, 0. So 0, 0, 0 is E1 tensor E1 tensor E1, where EI is the standard basis for C2. So again, you've got this physicist's notation in something that you follow. So it's just shorthand, right? If I have a basis for C2, or I'll just say H, if I have a basis for H, obviously that generates for H, tensor H, and I'm just going to be using this notation to basis. Okay, cool. So if this once upon a time was 0, 0, 0 plus, and then we had a bit flip error where the second bit got flipped, then you can see that this becomes 0, 1, 0 and 1, 0, 1. Now we want to be thinking about these the interiors of these as kind of invisible, right? So it's like we've received this and we just want to see a projective measurement whether there was a bit flip error or not. So we know that there is one, but how can we get the maths to see that there is one? And what we do is we do 2 measurements. We're going to do Z1, Z2, and then we're going to do Z3, and we're just going to see what happens. So the probability of the outcome is given by this, and we can just go ahead and compute this. Okay, so now I actually do mean the dual element here. So that's the bra notation, was mentioned in the previous talk.
I can't understand what you wrote there.
Really? So I've just gone A bra 010 and then plus B bra 101. Is it too messy? Is there stuff covering the screen that I can't see or something? Let me just write it more neatly.
No, it's good.
Okay.
It's fine for me.
Sweet. Wait, actually, I've got these the wrong way around now. Okay, third time lucky. So what is it? 0, 1, 0 first. Okay, so let's just go ahead and perform Z1, Z2 on this. So the first bit stays the same. And then we can see that, well, if I perform Z1, Z2 on this basis vector, it's going to bring out a -1 corresponding to the fact that the second bit is a 1, right? And then here, that's coming from Z2. And then here it's going to bring out a -1 coming from the fact that the first one is a 1. So that's coming from Z1, right? So both of these actually become negated. And so this simply becomes -A 0, 1, 0 minus B 1, 0, 1. And then you can see that, I mean, this vector applied to its dual, so it just becomes 1, but it's going to be 0 over here. And then similar story for B. So this whole thing simply becomes -A squared minus B squared. And so if A squared plus B squared was 1, which I should have assumed at the very start, right, because we're representing qubits as norm 1 elements inside this state space, then this measurement comes out as a -1, right? And so the point is, we've performed this measurement, and so we're like, oh, whoop-de-dee, great. And then what we do is we do another measurement upon this measurement, and that's going to be Z2, Z3. And when we do that, we get another -1, right? And if you just think about the logic of it, if performing the measurement Z1, Z2 to that gave me a -1, then that means either the first bit or the second bit has flipped. And then if Z2, Z3 gave me -1, then that means either the second bit or the third bit has flipped. And so since either the first or the second and either the second or the third has been flipped, we can see that the second one has been flipped, if we make the assumption that only one of them has been flipped. Okay, that's great and all, but then the problem is, maybe what happened is we completely destroyed the message when we did that. And this is the point that I was trying to make earlier. In fact, we haven't. So performing Z1, Z2, that measurement does affect the qubit, but then Z2, Z3, it actually kicks it back to where it was originally, which is pretty cool. But it's 11:34, so I probably don't have time to do that calculation. Happy to do it somewhere else in some way.
Yeah, maybe in the break you can do it if someone's interested. But yeah, let's try and wrap this up in a few minutes, maybe.
Yeah, sure. Okay, so I mean that's essentially it. You've got this method of performing error correction or error detection. At least I did use this assumption that only bit flip error has occurred. In fact, there's like more general theory out there. The theory of the stabilizer formulation will actually tell you that the bit flip errors are the full set of errors that can possibly occur and be detected by this family of measurements, which is pretty nifty. And that more general theory, Dan and I are trying to do something relating that to this program, geometry of interaction. I've absolutely no that now. I'm not going to. But anyway, hopefully that's a good little introduction. I think I'll end there. Thanks for listening.
Yeah, thanks, Will.